Okay, hi. So my name is Nicholas, and I'm going to be talking about my paper towards evaluating the robustness of neural networks. And this is joint work with my advisor, Dave Wagner. So before I start talking about anything related to security, let me give you a little bit of background on the machine learning side of things. So for the purposes of this talk, I'm going to be focusing on neural networks, which you can basically think of as a function with some trainable parameters that's going to learn some kind of mapping. So this might be given an image, classify it as a cat or a dog, given a review, classify it as good or bad, given a file, say it's malware or benign. Neural networks can do many types of things, but for this talk I'm going to look at just the classification side of things. So just neural networks for classification. So the image everyone always shows you when they want to show you a neural network looks something like this. And the idea is very simple. We have basically a graph with weights on the edges where we're going to put values in the nodes. We start out by feeding the input with some kind of raw representation of the values. So I'm going to be looking at image classification in particular. So we're going to feed in the raw values onto the very left. And then what we're going to do is we're just going to take these values, multiply them by the weights, add things together, and go layer by layer, computing the values at the next layer, and the next layer, and the next layer, until finally we get some outputs. And if we did it exactly as described here, that would almost work, except for the fact this would be an entirely linear function, and that wouldn't be very useful. And so instead what we do is we apply a single nonlinearity at some of these intermediate nodes. The most commonly used function here is known as ReLU. It's basically just take the max of 0 in the original function. And then we end up with something that looks sort of like this, where we apply some initial inputs, do some multiplications and additions, and a single nonlinearity at every node. But we do a lot of those, and so we can represent basically any function we want with neural networks. So the output of a neural network is going to be a probability distribution over the values. So if we have output being P and Q and some other things, then we say that P is the probability of class 1 and Q is the probability of class 2 and so on for all the other outputs. In order to train a neural network, we define some type of loss function, which is a measure of how accurate the network is. The idea is the loss function is very small if the network is very accurate, and the loss function is high if the network is not accurate. And then we use a process known as gradient descent in order to actually make the network something that's useful. So what we do here is we start at some random point in the space, and we slowly take steps trying to minimize the loss function at each step. So if we start off somewhere here in the middle, we'll go a little bit closer to a minimum value, take another step, go a little bit smaller, a little step smaller, and keep going until we end up with something which is a reasonable approximation of the smallest value we can find. So this is basically everything you need to know about neural networks from my talk. There are sort of two important things. The first thing you need to know is that neural networks are highly nonlinear, and the second thing that's important to know is the process of gradient descent. Okay, so that's what neural networks are. Now let's talk about why we care about them. So the ImageNet contest is a relatively famous contest. It was released in 2009. The objective is you're given some type of image, and you want to classify this image into one of 1,000 different classes. So this image is of a dog, and so the output of the classifier should be dog. And there are 1,000 other classes. There's school bus and hummingbird and everything you can imagine. So in 2011, the best team in this contest managed to get 75% accuracy, and no one was using neural networks at this time. 75% accuracy is still reasonably accurate, but there's a lot of game we can still have. And so the following year, one team decided they were going to try using neural networks and increase the accuracy to 85%, nearly bringing the error rate down by a factor of 2. Only one team used neural networks in this year, and they did the best. And so the power of neural networks can be seen by the fact that the following year, every single team that had a top submission used neural networks. So we go from no one using neural networks in 2011 to everyone using them in 2013. And neural networks are really powerful, and today we have 97% accuracy on this contest. So really, neural networks give us the best results. If you can think of any task that you want to apply machine learning to, chances are neural networks give you better accuracy than anything else. So that's all great and everything, but this is a security conference, and so I'm going to tell you that there's a catch. And the catch is that neural networks are very, very easy to fool. And in particular, what I'm going to say is that if you give me some image x and any label you want t, then I can find an input x prime, which is very close to x, but so that the network, when classified on x prime, will tell me label t. This is sort of bad. It means that if I show you these two images of a dog and ask a network to classify them, it will tell me the one on the left is correctly a dog, but tell me the one on the right is a hummingbird. And clearly this is not. None of us would say this is a hummingbird, but this network has made this decision. And so what this talk is going to be talking about is how I managed to do this. What do we do to actually make this possible? So, brief threat model. I'm going to assume that the adversary has complete access to the model and all of the parameters. Some good work has been shown that actually you can relax this assumption, but for the purpose of this talk, let's just assume that the adversary has complete access to the model. And their goal is going to be to construct adversarial examples, to construct these fooling images on this network. The other thing to know about adversarial examples is there's been a huge amount of work attempting to prevent adversarial examples from networks. This is just the papers I'm aware of from the last year and a half that try and remove adversarial examples from neural networks. And there's a lot of it. And so the question is, which of these are good approaches and which of these aren't good approaches that can be broken? And so for this talk, what I'm going to be focusing on is asking the question, how should we evaluate if a defense is actually effective? How do we know which of these defenses work and which of them don't? So to do that, you can consider, in general, two different ways of evaluating robustness. The first way you can evaluate robustness is to construct a proof. And you can say something like, for any two inputs that are closer than delta, their outputs differ by no more than epsilon, and therefore the network is secure. And that would be great, and some people have tried that. But the main limitation is that these approaches scale to network with tens or maybe hundreds of neurons. But the approaches we use in practice have millions of neurons. And so we really are 5 orders of magnitude away from being able to use these approaches in practice. So what I'm going to focus on doing on my talk is constructing an attack and say that if you can apply this attack to your defense and it succeeds, then the robustness of your defense is no greater than whatever I can do with my attack. So how do we mount this attack? Well, we basically have 2 key insights. The first key insight is that gradient descent, which is the process we use to train neural networks, works very well. And so can we just try and use this approach to attack them too? So we try to do this. And to do that, you're going to need some kind of function you want to minimize. And so the function I choose to minimize looks something like this. And what it's going to say is I want to minimize the distance between the valid image x and the adversarial example x prime, such that 2 things are true. The first thing that has to be true is we have to have that x prime is actually classified as the target class T that I want. Otherwise, it's not an adversarial example. And the second thing is that x prime has to be a valid image. Where by valid here, I just mean relatively simple thing that like each pixel value is discrete between 0 and 255. So you can try this. You apply gradient descent to this and see what happens, and you would realize that it fails completely. And the reason why it fails in this case is that these nonlinear constraints are very hard. Gradient descent works well over smooth boundaries, but we're evaluating a neural network in the constraint, which makes it very, very difficult. So instead what we do is we take a trick from the convex optimization literature, and we move the difficult constraint into the objective function. And so we give a reformulation that looks sort of something like this. We're still going to minimize the distance between the valid image x and the adversarial example x prime, but now we're going to also introduce some new function g, which we're going to apply to the adversarial example x prime. We still have the one constraint that the image is valid, but this is sort of a nice convex region, so that's easy to handle. So the question here is, what is this function g? The function g is just some kind of loss function that describes how close we are to being classified as t. With the idea being that if g of x prime is less than or equal to 0, then we have that f of x prime is being classified as t, and if g of x prime is greater than 0, then we're not yet classified as t. And hopefully it's sort of smoothly interpretable in between these 2 results. So what's an example of this function? Well, one example that you can think of, which is sort of the simple example, is to say we'll take the network, we'll evaluate it on this input x prime, we'll look at the probability of class t and subtract that from 1. So what does this look like? Well, if the network f of x prime says the probability of t is 1, then we end up with 1 minus 1 is 0. And conversely, if we say that f prime says the probability of t is 0, then we end up with 1 minus 0 is 1. So we're maximized when we're not an adversarial example and minimized when we are. So that's the first important thing to do, is to use gradient descent to just do this formulation for us. The second thing that's important is that actually the loss function you choose is very important. And in particular, the previous loss function I gave you is actually not a very good loss function. And formulating a good one is relatively difficult and requires some math, And so I'm not really going to talk too much about that in this talk now, but the details are all in the paper. So now let's talk about how we evaluate this. How do we know if this approach that I've given you is actually effective? Does this actually work? And again, in the paper, there are all sorts of tables and everything, but that's not really fun to talk about. So let me give you two different ways that I can evaluate this in a talk. The first thing I can do is I can compare this to other attacks. So people have published previous methods of generating these types of attacks, and I can compare how well we do compared to how well they do. So what I'm going to do is I'm going to show you some image here. This is an image of a handwritten digit 7. This is from an image classification task where we're given handwritten digits from 0 to 9. You have to classify what the digit is. The previous state of the art could give you something like this, where you modify the image, relatively noticeable modification to produce a different image, which is now classified as an 8. Our attack can do somewhat better and only make a smaller change. But this is sort of in the best case. In the worst case, if you want to turn this image into a 7, from a 7 into a 0, previous attacks would have to make a relatively large change and destroy most of the image. Our attacks make a much smaller change and are still effective at constructing this image to make it a 0. So this is sort of on one small data set benchmark. Let me again show you the same image I showed you earlier, where the image on the left is classified as a dog, and the image on the right is classified as a hummingbird. This is generated with our attack, and it's the first attack that can generate effective attacks on images of this size, where we're minimizing the total number of pixels changed. Since it's probably pretty hard for you to see the distortion here, let me zoom in a little bit on the face of the dog. And you might be able to see that there are a couple of pixels here where we switched the pixel from one value to something else. In total, we switched about 200 pixels of several hundred thousand, so the total distortion is about 0.1% of the pixels. The other important thing to note is that these images are classified more strongly as the adversarial class than as the original class. So neural networks will give you confidence results back, and will say with what confidence it thinks that the classification is. And so in particular, for this neural network, it will think that the confidence of this dog is only 83%, but it's 98% sure that this thing is a hummingbird. This is not unique to my results. This is sort of a general thing that's well known, is that you can do this with high confidence. So the other way that you can evaluate attacks is then to try and break existing defenses. And for that, what we do is we look at that list of defenses, and we say, let's look at the strongest one that was available, and let's try and break that one. And so the strongest defense that we were aware of was a paper that was published last year here called defensive distillation. And what we show is that when we apply our attack to this defense, we completely defeat this defense and show that it basically adds very little robustness. So if we look at the same plots of images, here I have some digits, handwritten digits of a 3. Previous attacks fail almost entirely on defensive distillation. The success rate goes from 99% on valid images to less than 1% on images, 99% on undefended networks to less than 1% on networks that are defended with defensive distillation. Our attacks, though, succeed still with 100% probability, and the distortion is not significantly larger than on the original inputs. OK, so then let me give you all a brief conclusion. You're building a defense. What should you do to evaluate it? There are basically two things you should do. The first thing you should do is you should release your source code. This is very much an empirical science. It's very hard to tell, given some description of an algorithm, whether or not it works. By releasing your source, you make it so that other people can effectively evaluate your defenses, and someone like me doesn't go have to re-implement it and can just look at the actual implementation. And the second thing you should do is you should evaluate against the strongest attack possible. Today, that means you should evaluate against the attack that I'm presenting here. But in the future, when someone else comes up with a stronger attack, you should be evaluating against theirs. Robustness against weak attacks does not exactly tell you very much. As we saw with defensive distillation, it succeeded with basically 100% probability against weaker attacks. But against stronger attacks, it failed with 100% probability. So given that I said you should release source code, I have released all of my attacks online. I encourage you to take it, look at them, download them, and use this against your defenses. And hopefully we can use this to construct better attacks and better defenses. Thank you very much, and I'll now take any questions.
Hi, Cristina Anita Rotaro, Northeastern University. Thank you very much. This was very, very interesting, and I'm very happy to see that people started taking attacks against machine learning seriously. Can you comment on the cost slash overhead of creating the attacks that we talked about?
Yes, sorry, I should have mentioned that in my talk. So the approach that I take is relatively slow. It takes, maybe 30 seconds or a minute to generate an attack. There are approaches, there's some that generate attacks much more rapidly, but the results are about 4 or 5 times worse, depending on which, maybe you can get around 2x worse, depending on what you do. It depends on what your goal is. If your goal is to generate attacks that evaluate the robustness, I don't think time should really be important, as long as you can do it relatively efficiently. A couple hours, I think, is reasonable. But if your goal is to try and actually use these attacks for some real-time process, maybe you care about time, but I don't think it's all that important.
Thank you.
Yeah.
Hi, my name is Sahar Mazloum from George Mason University. Thanks for your nice talk. My question is, I don't know if I missed that part or not, but I understand that the goal is you want to minimize the number of perturbations that you make to an image, right?
Yes.
But how did you choose the pixels that you want to change the values?
Okay,
Did you run another machine learning or?
Yes, so that is a good question. So we show that, so there are a bunch of ways you can call two images close. We look at 3 different distance metrics. One of them is L2, which is standard Euclidean root mean square. The one I showed you are examples what's known as L0, which you want to minimize the number of pixels. So for that one, we have an approach that basically starts off by letting you modify every pixel and slowly shrinks this set of modified pixels until you end up modifying very few pixels. And finally, something we can do is we can modify under a different distance metric where we instead say that we want to not change the fewest number of pixels, but make the smallest change to each individual pixel. So I have a slide for that shows this one. So whereas previously there were some pixels that were very clearly changed, if you make a change to every pixel by only a very small amount, I can do this by only flipping the lowest bit. And so in particular, I can only flip the lowest bit and target any class you want. And so this is something that other people have shown too, but it's sort of a different distance metric, whichever one you consider most useful.
Hi, Nicola Paperno from Penn State University. Thank you for your talk. In your presentation, you assume a white box threat model. And could you comment on the strength of your attack in black box settings?
Yes. So basically to use the attacks where you don't assume the model, what you do is you use the approaches that you've actually done, and you train your own model. So I assume the defender has their model. And what I'm going to do is I'm going to train my own model in sort of a similar way that they used to train theirs, and hope that the 2 models end up learning sort of the same decision boundary. And then what I'm going to do is I'm going to generate an attack on my model, and then it turns out there's a property known as transferability, that the attack on my model actually is effective on your model. And so if I don't actually know what your model is, then I can use this approach to still attack your model even if I don't have actual access to the parameters.
I guess my follow-up question is, have you compared the main perturbation of the inputs that you produce in black box settings and that transfer to other models?
Okay, yes. So do these approaches work to transfer? So yes, so you can actually, with the approach that I've outlined, control the confidence of the attacks and use it to generate attacks that do transfer. In order to make attacks that transfer effectively, you do need to increase the distortion. How much you need to increase the distortion depends on the defense and depends on how close you can actually get to the other model. So if you assume that I know nothing about the other model, then the distortion needs to maybe increase by a factor of 2 or 3. But if you assume that I can sort of oracle queries against the other model, then you can reduce that by a fairly large amount.
Okay, thank you. I just want to mention that we have a poster this evening on extending defensive distillation to mitigate some of these attacks. Thank you.
Ellie Canal, Software Engineering Institute. Thank you for an interesting talk. One thing which I noticed about your technique is that it will always eventually perturb the image to a point where something will be changed. So is there a way that you can assess a metric by which here's the amount to which we need to perturb the image so that we can actually fool the model?
Yes, so there are sorts of two types of attacks. There are attacks that will always succeed by just eventually just turning the image into something that actually recognizes the other class, and just you're trying to minimize the total distortion. And there are another type of attacks that say you can only distort by this much and just do as best as you can. And so my approach takes the former approach and says that we'll try and minimize the total distortion. And if you want, you can just set a threshold at any given point and say, if I've done more than this, you just report failure. But since the objective is to minimize the total amount of distortion, it very rarely fails.
Thank you.